Hi, welcome to another lecture on Calculus 2. Topic today is area and arc length for parametric curves. So our plan was to redo a substantial portion of calculus for parametric curves. In the last lecture we talked about maximum, minimum, tangent line and second derivative. And today we are going to talk about area and arc length. This is going to be a bit more straightforward. So suppose we have a parametric curve that is given by x being a function of t and y being another function of t, and we are going from this starting point at t equal to alpha on this direction to t equal to beta. We want to find out what is the area underneath this, assuming that it is well defined, and also we want to find the length, which means the length of this arc. In that case, we are assuming that we are not doing any back and forth motion, rather we are going straight from beginning to the end without traversing any point more than once. Well, area, we remember from calculus, was integral of y dx. The y represented the height and dx represented the thickness of this ribbon, and y dx was the area from the starting point to the ending point. Now our y is just g, and dx, differential of x, will be derivative of f, which is f prime of t dt, and then we have beginning and end according to the parameter t. So here x will start at some a and end at some b, but for t we have alpha and beta, and that's all there is to it, to calculating the area. As an exercise, we go ahead to a famous curve that we looked at a couple of lectures ago, and that was the cycloid. You remember for the cycloid, so the question is find the area of cycloid, which was given by x is equal to r times theta minus sine of theta, and y was given as r times 1 minus cosine of theta. You remember the cycloid had an appearance looking like this. If you take a coin and roll it on paper without allowing it to skid, then it's going to have a curve looking like this. Now the question is, we're trying to find out what is the area underneath this, and you remember one cycle of this cycloid goes from theta from 0 to 2 pi. So I have y, I have x, I need to find y times x prime. So y, or g of, so this is my g of theta, and this is my f of theta. I need g of theta times f prime of theta. So g of theta is of course r times 1 minus cosine theta. F prime, that's another r times the derivative of theta with respect to theta is just 1. Derivative of sine is cosine. We need to integrate this thing from 0 to 2 pi. So that is my integral 0 to 2 pi of this. Well, of course r squared comes outside, 0 to 2 pi. I have 1 minus cosine squared, so that's going to be 1 minus 2 cosine theta plus cosine square of theta d theta. I want to calculate this integral. Let's go ahead, remember the identity that cosine of 2 theta was cosine square of theta minus sine square of theta, which can be written in two other ways. Let's just practice this thing. You can write it as 2 cosine square of theta minus 1, or 1 minus 2 sine square of theta. What I'm planning to do is to convert this thing to cosine of double the angle and integrate like that. You have other options available to you. So cosine square of theta is 1 plus cosine of 2 theta over 2. So the area we are calculating, area is going to be r squared, 0 to 2 pi, 1 minus 2 cosine theta plus 1 plus cosine of 2 theta over 2, all of that d theta. Rewrite this thing again. R squared 1.5 is going to be 3 halves, minus 2 cosine theta, and then 1/2 of cosine of 2 theta from 0 to 2 pi. We already can see what's going to happen here. Cosine and cosine of 2 theta are going to go through a full cycle, so their positive negatives are going to cancel each other out, and only this component is going to be left out. But let's go ahead and calculate r squared, 3 theta over 2 minus 2 sine theta plus 1/4 of sine of 2 theta between 0 and 2 pi. At 0 and 2 pi, these are going to be 0, and all that we are going to be left is r squared times 3 times 2 pi over 2 and minus 3/2 times 0, and of course 2's cancel, we get 3 pi r squared. So the area of a cycloid is 3 pi r squared. Remember, the cycloid is obtained by rolling a circle. This is the area of the circle, and rolling it makes the area becomes 3 times as big. So that was straightforward. How about example of length? Suppose I want to find the length of a curve. For the length, we already had looked at this issue before. If you have a curve, you are going over it once, you want to find the length, you go ahead and subdivide it to straight lines. So these are line segments. This is going to be your delta x, this is your delta y, and this is, say, your delta s. I will say delta s is delta x squared plus delta y squared. I go ahead and divide this thing and multiply it, delta x by delta t, well, let me make a correction here. Delta s squared will be that, and delta s itself is square root of this quantity. So this is square root of this quantity, and I have to cancel the delta t, so that is going to be my delta t. In the limit, when deltas go to 0, we'll have element of length to be delta x, delta t, that's f prime of t squared. Delta y delta t is the derivative of y, that is g prime, and that has to be squared. And then our element of the parameter. So the length that we want to calculate, again assuming that we are going from alpha to beta, is going to be derivative of x squared, derivative of y squared, multiplied by dt, and then integrate it. Now let's go ahead and do an example. Let's go ahead and take the same example as before. We had for a cycloid, so here's a question, find the arc length of cycloid. So x we said was r times theta minus sine theta, y was r times 1 minus cosine theta. So x prime, or the same as f prime, is r times 1 minus cosine theta, and y prime is going to be r times 0 minus sine theta. What I need to do is x prime squared plus y prime squared. So that's going to be r squared times 1 minus cosine theta squared, and then r squared, and this is of course just sine square of theta. I open the first one, I'll have r squared times 1 minus 2 cosine theta plus cosine square of theta, and then I have another r squared sine square of theta. Sine square and cosine squared becomes 1, added to 1 gives us 2, so this becomes r squared times 2 minus 2 cosine theta. Now just a second ago we had identity, cosine theta is 1 minus sine, so cosine of 2 theta we had 1 minus 2 sine square of theta. So rearranging this thing, it tells us that 1 minus cosine of 2 theta is 2 sine square of theta, or 1 minus cosine of theta to 1 minus cosine of theta will be 2 sine square of, this is going to be half of that, theta over 2. So I can write this in r squared, multiplying this thing by 2, it becomes 4 times sine square of theta over 2. So what we have, x prime squared plus y prime squared in square root is going to be square root of r squared is just r. 4 gives me a 2. This one is going to give me sine of theta over 2 in absolute value. But if theta is ranging between 0 and 2 pi, theta over 2 is going to range between 0 and pi, and therefore this is going to be always positive. So I can write it simply as 2r sine of theta over 2. Now the length is going to be 0 to 2 pi of this, which is 2r sine of theta over 2 d theta. You can factor 2r. Antiderivative of this is going to be minus 2 cosine of theta over 2. Check that this is antiderivative. And then between 0 and 2 pi, you can write 2r. Let's put this minus 2 aside. And then cosine of 2 pi over 2 minus cosine of 0 over 2. So 2r minus 2 minus 1 is another minus 2. I get 8r. So length of a cycloid is 8 times the radius that generated it. as a matter of comparison, the circumference of the circle is 2 pi r, which is about 6 r. For the cycloid, by the time we go from one end to the other end of it, this is equal to 8 r. So 2 facts about cycloid we found today. And to go back, we have 2 basic formulas here. Just remember that double check end and starting and end of your region, making sure you're not going in reverse. Other than that, it's straightforward. Okay, until next time, good luck and God bless.